Okay, so first couple comments in general about the energy unit. I already mentioned this used to be Physics 30 curriculum, and so a lot of the questions that I'm going to find for you, I'm going to actually base off of the old Physics 30 curriculum, because honestly, energy actually hasn't changed all that much in the 7 years since they changed the curriculum. Like, it's still the same thing. So I'm going to give you a lot of diploma type questions this unit on your assessments, which will kind of be nice as a way to kind of see what a diploma question looks like. I make pretty challenging tests as it is, so I don't think it's going to be like a big jump, but you'll actually be able to see, okay, this is what kids in the past have been asked on a diploma exam. The other concept I need you to know is that, here, let's see what's sitting here. You guys know how on your formula sheets, there is a physics principles little section on the side there? We've talked about it a bit before. Like the first one is uniform motion, the second one accelerated motion, or actually one acceleration motion, two uniform circular motion. From here on out, we're going to spend a lot more time talking about theories in terms of like physics principles. So today, tomorrow, the next couple of days, we're going to be talking about concept number 3, number 4, number 5. We're talking about work energy theorem, conservation of momentum, conservation of energy. So that's kind of where we're leading to, is a lot more of like the theories. You guys probably know the concept of work energy at some point, right? We've talked about that, how work is energy and energy is work. So it's kind of a different way of approaching your thought process. One way of approaching a question is from like a kinematics dynamics point of view, where you consider things like distance, acceleration, velocity. All of those things, what they share in common is they're vectors. For all those things, direction matters. But there's another way of approaching things from the energy point of view. And what's unique about the energy point of view is that they're not vectors. Energy is not a vector quantity, it's a scalar quantity because it really goes in whatever direction. Do we want to lock that up there to reduce the sound? It's distracting. You guys remember the difference between vector and scalar? Okay. Today is more or less a review day. We're not doing really a whole lot that's new. We're going to talk about basically the different forms of energy and a couple of formulas associated. This is kind of what I was hinting at. Energy is a very different way of thinking about how the world works. Kinematics and dynamics are basically Newton's laws in a way, focusing on forces, velocity, acceleration, distance, all of your basic vector principles. Energy is another similar way, but it's a different approach. You're now approaching it from a less directional point of view, and it's hard because I can't think of another word to use in place of energy, because energy is kind of the word we'd use. It's from an energy point of view. Right? Kinetic, potential, light, sound, heat, electromagnetic, all of the different types of energy that you can have. More or less, I mean, there's the two main categories. You guys have seen these before, right? Kinetic, potential. One is an active energy, something where it's actively doing something. One is potential, where, I think of a better synonym than potential, right? I mean, it's going to do something in the future. You guys good with that? Okay, so here are some basic formulas that you've used at some point, I hope. If you want to find kinetic energy, 1/2 mv squared. If you want to find potential energy, due to gravity, by the way, gravitational potential energy, mass, gravity, height. Those are kind of your basic ones from grade 10. Big difference I've already been mentioning here. These are directionless. We don't worry about what direction this is traveling in. If I huck my pen across the room, it's got a different x and y component the whole time, but we just find just the instantaneous velocity at any given moment. We don't really care about direction. One of the reasons why energy can't have a direction is that, although maybe you could argue that gravitational potential energy is pulling it down, yeah, maybe you can make that argument. Other forms of energy, they don't go one way, like the lights. That light energy is really traveling in all directions. We're gonna refer to the concept of a field a little bit later. Remember gravitational fields, how like they all pull like inwards? Remember drawing that in the lab? Right? I really can't give a direction to that. That's not really north, south, east, or west. It's not really up or down, because it really just depends on your perspective. I think I made the point. Okay, let's try some really basic examples. Shelf in your locker is 1.8 meters above the floor. Here's your textbook mass. Did you figure out how much energy the object has? This will be your gravitational potential energy, which is mass times gravity, energy 1, times height. Say that. Two times 9.81 times 1.8. I got 21 and change. Sig digs, we need 2. Remember the unit for energy? There's a second unit for energy I need you to know. Anybody know that one? Other than joules? A second unit for energy, the alternate one. Nice, good job. Newton meters is the other one. Let's talk about that one for a second. There's a theorem you've already learned at some point. You probably forgot, but maybe you've heard it. It's actually one on the sheet that's next. It's called the work-energy theorem. If I were to ask you from a physics point of view to define the word energy, energy is such a weird word to define. The definition of energy in physics is the ability to do work, which seems so silly because it's like, well, then why not just call it energy? Well, they are the same thing essentially, right? Like if you can do work, you did work because you had some energy. Right? Or if you use your energy up, it's going to do some sort of work. They're really like synonymous with each other. Does that make sense? So the unit for energy is typically joules, but it's equivalent to the unit for work, which is Newton meters. So did you know them both? Why don't we break that down actually into its base units? This right here was a meter. This was a meter per second squared. And this was a kilogram. So if you ever get asked what like the basic units, like the fundamental smaller broken up units are, it is a meters squared per second squared times by a kilogram. Those are essentially its core fundamental units. You either write it as a joule, or if you pull a meter out of it, it's a Newton meter. Because a Newton, if you guys remember, a Newton is a kilogram meter per second squared. So if a Newton is a kilogram meter per second squared, if you times it by a meter, hopefully you can see how you have like the extra square on the meters there. I don't care what units you use, but make sure you're aware of both. Okay, let's save some time here. Let's not actually calculate them. Let's just talk how we solve them. This one would be kinetic energy. It would be 1/2 of mv squared. You guys feel like you could pull that off? You're given the mass, you're given the velocity. What would you have to do to the velocity though? You gotta convert to meters per second. That's all. Good with that one? Okay. What about this one here? This is a baseball with a mass of 145 grams moving at a speed above the ground. What's different about this example? What am I trying to show you here? Yes, 2 forms of energy. Okay. So once in a while we'll have to make sure we add them together. Okay. So you have to do your kinetic energy, which will be 1/2 of 0.145 times 18 squared. Guys catch how I converted from grams to kilograms? But you'd have to add to that your gravitational energy, or however you want to designate the little thing in the corner there, which is mass times gravity times height. So take your kinetic energy and add your potential energy to it. Don't forget to include both. Which one are you looking at, Eddie?
What was the bottom one say?
Sorry, this was plus EG. I was going for gravitational energy. Maybe put a P there. I don't really care what letter you use. Does that make sense? This is your mass, your gravity, and your height. And this is your mv squared. That makes sense? Okay, so again, you can probably use your calculator to solve that. I'll move on. Here's our last one. What if you have a slingshot and you pull it back and I give you its constant? What is its constant? We just did this. K, yeah. I've given you a K constant for your slingshot, and I've also given you how far you pulled this back. which we often give another letter to, x. Well, we haven't learned this formula yet, so that's my next slide. Here's one we haven't covered in grade 10, but it's pretty straightforward. This is the potential energy due to a elastic. I'm sorry, I seem to have spelled the word elastic very poorly there. Elastic. So, anyways, the formula for a spring of any type, the amount of energy that it can basically turn into work, the amount of energy that it can use to do something with, is 1/2 of kx squared. That's very similar to kinetic energy, isn't it? Let's show why this is going to work. You guys remember the units for K are newtons per meter. The unit for X is going to be meters squared. You guys visualize how the newton per meter, the meter on the bottom will cancel with one of those ones there, giving you a final set of units of newton meters, which is equivalent to a joule. So it's pretty straightforward. If you want to go back to the last slide here, all you have to do is 1/2 of 156 times 0.068 squared. Don't forget to divide the 6.8 centimeters into meters. Otherwise, it's not actually a joule. You wouldn't actually have a centijoule because it was squared. You'd have like anyways, it wouldn't be a joule. So far, so good. What we're going to do in Physics 20 is we're going to work independently with a whole bunch of the formulas off your data sheet in the energy section there. You guys can see how there's EK, EP, and EP. Okay. So in Physics 20, we're going to work more or less just with those formulas. But you're going to use them again in Physics 30 with anything else that involves energy. Okay. Now, there's not a whole lot of them on the formula sheet, but let me point out a couple if you guys can visualize down here. You guys see in the atomic energy section down there, at the very, very bottom, you can see there's an EK max formula. So we're going to use kinetic energy again in Physics 30 and atomic physics. And if you go up one and over one, there's a formula that goes E equals HF. That will also involve energy as well. Up in the very, very top corners, under quantum mechanics and nuclear physics, there's energy equals mc squared. That's Einstein's formula. Next to it, there's E equals PC. So you guys can see how there's different formulas that involve energy with them in the future. So what we normally do in Physics 20, we use just purely the three formulas given in the bottom corner. In Physics 30, we will combine probably one of those formulas, depending on the context, with other formulas on the data sheet and merge them together to make new kind of scenarios. I got to point one more thing out though. If you guys see E in the electricity and magnetism section, E with a little line over top of it, you guys see that one there? That is not energy. Seems silly that we use the same letter twice, but there's a really, really important distinction there, and it's the little line over top. What does a line over top imply? It implies a direction, a vector. It is not energy with a vector, actually. It has to do with electric field strength. We only have 26 letters there. Okay, so just so you're aware, if you see those ones there where it's E, E, and E right there, those ones don't count. However, in that electricity and magnetism section, there's one that says B, delta V equals delta E over Q. See how that one doesn't have the little arrow over top of it? That one is energy. So make sure you're clear on which ones are actually involving energy and which ones aren't. Okay, let's move on. So here's our next theorem off the list of the theories. I already mentioned this. Energy, I mean, it's crazy that this is the best definition we have for energy. Energy is basically the ability to work. That's the best definition we have for it. Because energy is so varied. I just showed you that energy is basically something that was in every single unit. There was quantum, there was electricity, there was atomic, there was momentum and energy. Like literally every unit has energy in somewhere. Right? Light energy, sound energy, nuclear energy, thermal energy. We did energy in chemistry 30 last year. Right? So because of that, this is the best definition for something so broad. Energy is such a broad term that we're just going to say, well, energy is work. Okay? Which then means, well, what is work? Well, work is when a force causes an object to move through a displacement. You guys probably have seen this formula. Not that formula. work equals force times distance. You remember that formula from sometime before? So essentially, energy could be 1/2 mv squared, it could be mgh, it could be 1/2 kx squared, or energy could be force times distance. How much work are you doing when you sit in your desk? Really none, because you're not moving. Well, I mean, okay, maybe you're moving your hand, but right, in terms of big picture, right, unless you actually have a displacement, you're not doing anything. This scenario right here is also you doing no work, by the way. If you have a backpack on your back here with heavy books in it, the work you would be doing, well, the force that you're overcoming for the textbooks is gravity. But if you are walking in that direction there, it's not in the same plane. Does that make sense? So the next point I want to make is that not only do you have to use a force over a distance of some type, but the force and the distance have to be in the same direction. If they're not in the same direction, that doesn't really count. So A, you have to use some force. B, the force has to cause something to move. And C, the force has to cause something to move in the same direction the force is causing it to move. Which leads to our next formula. This is actually the official kind of work formula. When I give you guys work is force times distance in the past, I kind of lied. Kind of like, I say this sometimes, I tell you a lot of partial truths when we first learn things. The real formula is force times distance cosine theta. Only when we are usually working with something, our angle is 0 degrees. Cosine of 0 is 1. So normally when we've done this in the past, the angle we would have been doing is 0 degrees. If you type in cosine of 0, it's 1, which means we wouldn't have bothered with it. The reason why it was normally 0 degrees is because if I were to draw a triangle of which direction the force happens to be pulled at, normally pull it the exact same direction as our displacement. But what we're going to do now in this unit is what if we pull at like a slightly upwards angle, but what if it actually moves this way? You get the concept of what I'm going for here? Imagine that like I am trying to pull something this way here, but I don't pull directly parallel. What if I pull kind of up? You know where I'm going here? And it still slides along the ground, but really the work I do is only the angled proportion that's actually along the x-axis. So this right here is basically your angle right there. Here's the proof for how this kind of works. You know how like cosine is adjacent over hypotenuse? In a way, if this is your angle right here, there's your hypotenuse. Here's your adjacent. So like your force over like the x direction amount of the force would be equal to cosine of theta. So like you can just like times that up. That makes sense? Gonna get how this is kind of working here. So basically the formula is already made for you. If you want to figure out how much work you do, it's got to be force times distance, but it's got to be the cosine, so you account for it being the adjacent component. So let's try an example. It's actually not that hard. Suppose the box is pulled along the ground by a force and it's at an angle of 30 degrees above the horizontal. I didn't actually give any numbers, so let's just make some up. Let's say that the amount of force that you used was, let's say it was 10 newtons. So this is 10 newtons. Let's say that the distance that it traveled was 2 meters. So that means that this is 2 meters. Are our forces and our directions in the exact same plane of motion? No. So what we're really doing in this formula is we're kind of calculating how much of this triangle, how much of the force was actually in the x direction. Does that make sense? So anyways, we would just do this. Work is force times, what am I doing? It's time to be done for the week. Force times distance times the cosine of theta. 10 times 2 times the cosine of 30. That's it. So don't just do 10 times 2 and get 20. You'll have to do 10 times 2 times what cosine of 30 is. What'd you guys get? So 17 newtons? Not 17 newtons, 17 newton meters. Or you could have called that joules. Either one would work. So put a little note here. This was not equal to 20 because of the angle in the corner. That's all. Good enough? Okay. Let's try some more examples here. I think that's all I really have left, right? Just a bunch of examples. Oh, and my graphs. Okay, examples and graphs. Okay, so we've got a force of 8.1 newtons. It's pulling a 60 kilogram object along the ground over a distance of 2.3 meters. Find the work. We haven't been given any sort of angle here to indicate that we're pulling it like off kilter. So I think we're just going to have to assume that the force is in the same direction as the distance. So work is equal to force times distance times the cosine of our angle. But since we're pulling in the same direction, you can either just not use the cosine theta part, or if you really feel compelled to actually write it in, what it really is implying is that your angle is 0 degrees. There is no discrepancy. There's no like angle in between there. I'd like to show you guys a really common mistake. Some people think that force is equal to mass times, say, acceleration, which it is, times the distance, because force is mass times acceleration. They might say, mass, 8.1. Acceleration. Oh, sorry, no, that's right. Mass, 60 kilograms. Acceleration, must be gravity. Distance, 2.3. Why is that wrong? It is in the y direction. But we're not pulling this thing in the y direction, we're pulling it in the x direction. That makes sense? Because acceleration could be gravity if it was a free-falling object. This isn't a free-falling object. I guess what you're saying is correct, in a way, right? So make sure that you don't somehow, if I give you a mass, try to like fit it into here unnecessarily. You can. It is possible that you'd have to find a force from a mass times acceleration. But in this example here, I already gave you the numbers you needed. You just needed, so all that's no good. You just need work is force times distance. We're good to go. $16 or $17? 19? No. Do we need a direction? We're not going to if we're talking about energy here. You will notice if you look at the formulas here, work right there, the W, does not have a little arrow on top of it. Even though a force is a vector, even though a displacement is a vector, because work is going to be considered equivalent to energy, we typically make work not a vector anymore. So don't need to worry about a direction on this one. So even if you threw it into Newton meters, either way, we're good. We're good in terms of vectors. There's actually a rule that if you ever get to a university course, you'll learn about how a vector times a vector becomes a scalar again. I don't remember how to prove why, but it's called the dot product. I remember that. I don't remember why. Okay, let's try another example. We have a force of 76 newtons, but now I gave you an angle. I gave you a distance. I guess feel like you could handle this pretty easily. Work equals force times distance times the cosine of your angle. You were given your force of 76 newtons. You were given your distance of 12.7. So this is work, but really work is energy anyways. So what'd you get? 790? So that. So then we'd have to do this. Everybody else got that as well? Awesome. Okay. Today's pretty basic. Really, this is a review of what we did in grade 10. With the exception of now you have to throw an angle in there, if there is an angle. There might not be. Okay, last thing. I gotta talk a little bit about how this works on a graph. Okay. If I were to give you a graph, and you had, say, force and displacement here, we haven't done this in a long time, but the area underneath the graph, like this area here, that would be equivalent to your work, or therefore your energy. The reason why is that area is equal to, like, say, length times width. Consider your units. Your length of, like, this square would be in meters. Well, let's change it up, actually. Let's do it the other way. Your length, let's call this your length. Your length would be in newtons. Your width would be in meters. Do you guys remember doing this in our very, very first unit? We had to find area underneath the graph. Now, the slope, by the way, on this graph doesn't mean anything. So there's nothing special to the slope of this one, but the area under the graph means something. So I don't know whether we will ever get to something like this, but if we were to do a lab and we were graphing how much force versus displacement there was, you might have to make some geometric shapes. Usually it's squares and triangles, just because those ones are easy to do. So let's try an example here. So this is something that you might see on a test. Find how much work was done or how much energy was expended. You could calculate the slope. That's not what we're looking for, though. Slope's not actually relevant to this graph. What we need to do is figure out how much this triangle really has for, like, area. Formula for a triangle. Area of a triangle is 1/2 of, like, base height. Unless it's crystal clear, we might have to make a little bit of an estimation here. How much for this base would you guys say it goes over to? I feel like it's slightly more than half. 110 is half. Like 112, maybe? I mean, there's no, on a graph like this, there's no really right answer, because there's a little bit of interpretation. I don't know. I'll go with 112. Thanks, Bert. And in terms of height, I think height is clear, though. That's 160,000.
Breakfast.
Anybody want bananas or yogurt?
There's vanilla, strawberry, and blueberry.
We're good. Thank you, guys. Appreciate it. You guys feel comfortable with this? What did you get? So, let's call it 8 point what? What's the next digit? Times 10 to the what?
49.
Oh, okay, so 9.0 times 10 to the 5? 6? 6? Sure, something like that. It's going to have to be multiple choice for something like this here, just because you will have a little bit of interpretation as to where the where this point exactly was. I thought 112. If you thought 115, we're close enough. So what I do need you to know is that on a work versus on a force versus displacement graph, slope's not really relevant, but area is. Okay? And we're going to see this a lot over the course of many of our future units, is that anything where it's something times something, the area under the graph is useful. Wherever it's something divided by something, the slope is useful. Say that one more time. If it's ever a formula where it's something divided by something, the slope is a very useful thing, because slope is rise over run. Does that make sense? If you ever have a formula where it's something times something, then you want area. So we'll do this actually on some of like our future labs. I mean, we're not there yet, but when we get to like the electricity and magnetism unit, See how there's a formula right at the beginning of it called Fe equals K Q1 Q2 over R squared. We're going to do a lab where we're going to try to calculate K. K is a constant. And we're going to do that by finding the slope of a graph, because you can see how there's going to be a fraction to that graph. Whereas, for example, in the atomic physics section, there's a formula that goes E equals HF. It actually goes on to also equal HC over lambda, but if we just do the E equals HF, if I gave you a graph of H and F, and we found the area of it, that would actually give you your energy. Okay. Questions so far? So far, so good? Great. For the first couple of days, you guys probably won't have very, very much to do. Spend your time getting caught up on anything you're not done. I mean, look at the first energy assignment, and if you want to give it a start, you can. There's going to be some questions that we haven't talked about how to do, but I bet you can solve anyways. That's all I got. You guys good? You look like you're good. Okay.